Hello F-sharp, and welcome back. We are continuing our work on writing a high-performance dictionary in just F-sharp. Now, I hinted that last time that we were going to achieve the best possible performance that I've been able to find so far, and that is still the case. So today is not going to be about how we can rewrite something to get better performance, but it's going to be a discussion on style and coding style and the implications on how our code runs. Because up to this point, I've been writing object code. F-sharp is not object-oriented, but it does support object programming. And that's what I've been doing for the most part, where I have been putting all of the functionality inside the class definition for our dictionary. Now, there's another approach, and I think of it as more of a C style of approach, and I actually prefer it. But to get the benchmarks out of the way, what we are seeing here is the result of our last benchmarking effort. It's the byte list Robinhood with inlining of that first iteration of the loop. And the reason we did that is we said the most common scenario is that that first bucket we go to is the one we are interested in. So we would rather avoid having to start up the loop infrastructure to iterate through possible buckets. And when I look at the performance of this next version, which I call the C style, it is using the same logic, but the way it is passing data around is slightly different. And when I use that technique, the performance is essentially the same. There's no significant difference between these two, which is to be expected after we go through this exercise of understanding how it works. So first of all, let me show you what that original version looked like in terms of the code. And I am in the Fast Dictionary Test solution, Fast Dictionary Test project. And if I go and look at byte list Robinhood inline, that is the one I'm interested in. I'm going to go ahead and close this for a moment. What we find is that I have the definition for my class, which is a dictionary. I give it the key value, and then all the logic is inside of this dictionary. And I use quite a few let-bound functions for being able to do this. And that is perfectly fine. I'm not saying this is bad. I'm not saying this is wrong. I'm just saying when I look at this, I start to get confused as I'm just scrolling and scrolling, and I have all these different functions for being able to add entries, look up entries. I have different functions for if the key is a struct type, like a value type, or if the key is a reference type, which means that the dictionary collection, that class definition, is quite a few lines of code, in my opinion. I'm still scrolling down, and okay, so we are at 400 lines of code in this file. That is actually not that much. Now, there are no really significant comments in here, so that would expand it. But in my opinion, this is having so many functions just thrown into a single class. I have a hard time following this because it's like, okay, well, where's the function for being able to do this? And one of the things I really like about the F-sharp language is that it has modules, and modules make it very easy for me to arrange code into groups of functionality that all work together to achieve an outcome. And modules can hold other modules, so I can nest that down to as much as I need to provide the clarity that I'm wanting to provide myself and to other users of my code to understand, hey, exactly how is this working? Now, the problem is, let's say if I wanted to divide up the functions for ref key related functionality and struct key related functionality, I can't do that inside of a class. So I said like module, my module, and let's say something, and let's say this takes a string, and I say like, hey, we just go print function s. Now, compiler's complaining, saying, hey, well, what is going on? Okay, well, this needs a format string. Well, okay, so we'll complete the exercise just to prove a point. So what's happening now is I have a module inside of my dictionary class, and the compiler is complaining. And rightfully so. It says namespaces cannot contain bindings. And what's going on right now is I'm trying to create this module inside of another class, and the compiler is going to say, no, this doesn't make any sense. You're not allowed to do that. Now, I would ideally like to say, hey, I'm going to have a module for my struct functions, and then all of my functions for working with those struct keys would be contained inside of this module. And then I would have a separate module for my ref key like functionality. So I wouldn't have just all of these let bound functions just all hanging out in the same space, because it's a little confusing, because I have, okay, let add ref entry, and then I have the add struct entry, and yeah. So ideally I would like to separate these things out. Now, the challenge is, okay, I could do that, but what happens when I need to call these functions with multiple parameters? And one of the things that we have found in this whole exercise is that when you have a collection and there's a particular method on that collection, and it is one of the hottest pieces of code in your entire code base, any amount of extra work is going to potentially significantly slow down your code. And one of the pieces of work that needs to be done is creating new stack frames. And what do I mean by that? So let's go to the drawing board to kind of explain what I'm talking about here. So we have this thing, which is the stack. And the stack just is an array of data, and it has values on it. And when you call a function, so I'm going to call a function one, just call this function one, and it takes an int and an int. Let's just say this takes two ints. And let's say I also have function two, and it takes a single int. And let's say function two calls function one. So inside of here, we're going to say, hey, let x equal to function one. And it's going to take, I'm just going to put in some values like 1 and 2, just to be silly. So when we call function two, we have the stack over here. And we have a pointer, which is pointing to like where we are in the execution of our algorithm. And so we could say like, hey, we're right here, and we push things onto the stack and we remove things on the stack as our program is running. But when F2 needs to call F1, what it's going to need to do is say, okay, well, if I want to call F1, what I need to do is I need these two values to be on the stack for F1 to do its job. And so when I make this call, what it has to do is say, okay, well, what I need to do now is I need to push 1 onto the stack, and I need to push 2 onto the stack. And now function 1 can be called, and function 1 can do its job. And when function 1 is done doing its job, then the function pointer will move back, and function 2 can continue running. This work of pushing values onto the stack so that you can call another function, that adds up. Now, it's so small in comparison to much of the code that we write that we don't really think about it much. But again, once we get down to these really high performance scenarios, and it's like, hey, if I'm having to call function 1, 1 billion times, and that means I'm going to have to push these two values onto the stack 1 billion times, that work will add up. And so what compilers do is if like this, and let's say like, hey, this is small amount of code here. So small amount of code. Let's say function 1 is a very small function. It's very fast and it executes very quickly. What the compiler will do, compiler writers know that this is a problem. I'm putting a problem in air quotes. Who say like, hey, if we are having to constantly create these stack frames and pushing values onto the stack so we can call other functions, that work adds up. But if we have these small functions, wouldn't we like to avoid that work of pushing values on the stack? And the way you avoid that work is instead of saying, hey, instead of actually calling F1, I'm going to take whatever code is in F1, and I'm actually just going to inject it into the call site. I'm going to put this into function 2. So instead of having to call this function, put values on the stack, run the function, then return a value, I'm just going to take whatever logic is in here and inline it into function 2. This process of inlining function or method calls is considered by some to be like the number one optimization for making your program run faster. It is, I should probably look at the quote of like who said it directly, but there's some like famous person in the C community said like, hey, this is the number one optimization. And I got this from, I don't remember the talk. I'll look it up, but this is a really big deal. But again, when we typically aren't thinking about this when we're running our high level business logic, but once you get down to this level of performance and we're trying to tune a collection, that is often the kind of the beating heart of our algorithms. So if this is happening too much, this is really expensive. So what we want to do is minimize the amount of work that goes on when having to pass values around. Now, the way we get around that when we are writing object code in F# is if I come up here and inside of this dictionary collection, I have declared all these values. I have my ref compare, I have my count, my buckets, my bucket bit shift, my wraparound mask. These values are all in context for all of these let functions. All of these let bound functions can see these values and work with them. So they're kind of like implicitly on the stack and available all the time. Now that's, whether that's good or bad is up for debate. It's a stylistic debate. I'm just saying how it works. So that's a huge convenience. When we have these functions that are mutating the internal state of our collection, this is great, having this kind of implicitly in context. But that is counter to our desire to be able to arrange these functions in such a way that it's easier for us to arrange the work. So how do we get around this? So what we can do is we could actually pass our, what I'm kind of consider like a context around as a struct and pass it around by reference. So you're only having to pass around a single pointer, essentially, a single reference to a piece of data. And that's what I kind of call the C style of writing this. So if I was actually writing C, it would look more like this. This is when I have this joke about like, hey, F# is my favorite language to write C in, because you can do very C-like things inside of F#. So what is different here? So I'm now on C style, and I have defined a struct which is internals. And internals contain all that state that I want to be able to pass around to the different functions. Things like the count, the number of elements that are in the dictionary, the array, which represents the buckets of the dictionary, the bucket bit shift that we need, is wraparound mask, and the comparer. And so now I have taken all of that, what was implicit state inside of the dictionary collection, and I've now created a separate type which holds all that state. And how do I actually use this thing? So what I do is I now pass it around as a reference, and I can do it. Oh, I don't want to rearrange. I can pass it in as an inref, which means it's a read-only reference, or I can pass it around as a by ref. But the point is instead of having to copy all the values in the struct whenever I want to make this call to this function, if I end up doing it, so let's say it's not inlined. If it actually ends up having to be called, instead of having to copy all of the values to the stack to create a new stack frame for that function to be called, I'm only copying a single int64 in this case, which is a reference to where this struct exists in memory. So that's a lot faster for me to copy, and there's a high probability of things being inlined. So that's fantastic. And so by passing around this internals struct, and I'm passing around by reference, I'm basically containing all of that implicit context in a single type. And now what does that let me do? That lets me have a struct module. And so inside of the struct module are all the functions for being able to work with struct keys for my dictionary. And then I have this get value. And now I have a module for the ref key like code. And so now I'm able to kind of separate out into separate modules the functions for working with these different types. So instead of having all those functions inside of the dictionary class, I have now been able to separate them out. But in order to get the performance on what I want, I am passing around the internal state of the dictionary as a byref to a struct. Again, this is a very C style way of doing things. And so when I come all the way down here to like, okay, where's the definition of a dictionary? This is all there is to the dictionary now. It has this internals struct where it's holding its internal state, and then it exposes the members that you need for being able to look up values and create instances of it. So at the end of the day, the external API will still feel very fsharpy. But the internals are taking advantage of byrefs, mutable state, and everything it needs to get the high performance that it wants. And so this is very much a stylistic thing. I would not fault anyone for writing a collection in this way, writing a dictionary where everything is kind of inside the dictionary and everything is right there. But for me, I wanted to go through the exercise of saying, hey, what if I separated things out so it's easier for me to find functions and see which functions are related to one another and work together? And how would I do that? How would I accomplish that? And this is how I accomplished that. At the end of the day, the performance between these two is exactly the same, because essentially what is going on is the exact same amount of work. It's just that I have taken that implicit internal state from that first style and have made it explicit. And like, yes, this is my state. This is the internals, and this is the thing that I am passing around and working with all the time. Again, all that mutation that's going on is hidden from the user at the end of the day. This is not what I would call very F-sharpy style, but that's if you're restricting your definition to F-sharp style to be only the, domain-driven design, immutable, everything style. This is part of what I love about the F-sharp language. Yes, it has these very pleasant defaults to work with immutable data, immutable collections, and piping data through. It's very easy to reason about. At the same time, the facilities are there for being able to write in a more C-like style to get the performance that you need and passing around structs by ref. So at the end of the day, we can accomplish the same thing all in the same language. So I thought this was a very interesting exercise to see what the two styles will feel like to work with. I actually found the C style to be easier for me to reason about because I was able to separate out all of these functions into modules that are all related to each other. Hey, all of these functions are meant to kind of work together to accomplish something. So hopefully that was interesting. I fun. I really enjoy style discussions, and this is like kind of style, also possibly architectural almost, and just like how are we arranging code and passing around data? Because at the end of the day, performance in today's machines, we are often bottlenecked by just memory bandwidth. So being able to minimize the amount of work that we're doing, moving things on and off the stack and moving things in and out of memory, that is what increases our performance. So I have a couple other things I want to show you in this series, but it's been really fun, and I hope you have a wonderful day. Thank you for spending some time with me. Bye-bye.